Hello, welcome back, everyone. Welcome to undergraduate seminar again. Aditya Chugh of the St. George campus is going to tell us about abstracting reality, symmetry ideas in physics. Super excited for this. Aditya, take it away.
Thank you so much, Professor. First of all, I'd like to say thank you so much for having me here. This is my first mathematical talk, so kind of nervous, kind of excited, but yeah, hopefully my goal is that maybe hopefully everyone learns something, at least takes away something that they find interesting. And yeah, just before we get started, I just wanted to get to know like what the sorry about that. Yeah, I just wanted to know what year people are in, like at least like other first years, second years, third years, like what's the
So what's people's back
year? I'm a third year.
Mhm.
second year
And yeah,
second.
right, okay. So yeah, I just asked because like I kind of wanted to gauge if people have done like multivariable calculus and stuff like that, if people are comfortable with like open sets and maybe like derivatives in higher dimensions, manifolds, that sort of stuff. But that's good to hear. Anyway, right. I think I lost my screen share, but I will do that again. Right. Okay. So that's the title of the talk: abstracting reality, symmetry ideas in physics. It is a bit dramatic, I would not lie, but yeah, it's just there's some really cool connections between math and physics and finding out at like a more fundamental level that the physical systems that we do see, that we do study, what can we learn more about them with some of the mathematical machinery. And even though we might have to stretch our imaginations in terms of, oh, this might be quite a bit abstract, but still there's still a lot of stuff to learn from this. At the beginning, just a little bit about me. I'm a second year student at the University of Toronto. I'm pursuing a math and physics specialist program. I'm originally from New Delhi. I like reading, playing soccer, the usual stuff. And I'm trying to learn more about mathematical physics. I really, yeah, like one of the major reasons that I did want to learn, they wanted to give this talk is to kind of find new stuff which would reveal connections between the things that I'm studying, between math and physics, and see how that stuff can be applied. So the outline of the talk is this. We're going to talk about symmetries at first. What are symmetries? A bit informally, not in very technical in a very technical setting, but that's how we start. Then we'll see how symmetries appear in physics, or at least how they might help us, and why they're nice. Then a very powerful theorem, Noether's theorem. That's quite a big theorem there, which helps us leverage some leverage how our system behaves, and from the symmetries find out conservation laws. And conservation laws are particularly nice to have. I'll give some examples of why they might really help simplify studying a physical system. Then, so the reason there are two parts is that you could, Noether's theorem has many formulations, and like you could start from a very physicsy definition of using calculus of variations, but you could really like things really go off the rails. Like you can study it in a very mathematical sense. Then and in that mathematical sense, there's they make the theorem makes use of something called Lie groups and Lie algebras. We will take a small detour with matrix exponentials just because they will help us they'll come later on in the very last section, which is a case for infinitesimal transformations. And it's just nice to know, and then it'll maybe help you appreciate more what we see there. So we'll get started. So symmetries at the very basic level, it's about balance, it's about proportionality, some sort of equality. Again, I'm talking about this in a very informal sense, but I have some shapes here, and you would consider a lot of them are pretty symmetric. I mean, there's the equilateral triangle, and you could consider how you might reflect these shapes, how you might rotate them, and that would reveal the symmetries of the shapes. So with an isosceles triangle, for example, which has two sides of the same length, you could say that if I reflect the triangle along this median, you would expect to find a similar shape. And that's one thing about the isosceles triangle. But I guess in some sense, the equilateral triangle is more symmetric, because not only you can find 3 of these medians, you can reflect along either of these, but you can also rotate the shape, and that would still look like it was before. So you could rotate it 120 degrees and it would go back, and you could rotate it 240 degrees, and this vertex here would go all the way over here, but it would still look like the original equilateral triangle. Then, and actually, not rotating or not reflecting is also a symmetry. It's kind of yeah. I guess the first time you see it, it's kind of bizarre, but not doing anything, just the shape, the identity, I guess, would also be a symmetry. Then, of course, a square, pretty symmetric, arguably more symmetric than an equilateral triangle. But yeah, and as you increase the number of sides of the shape, you'll see for general n-gon, I guess you might find that they look more symmetric, quote unquote. But then you might say, okay, what about a circle? I mean, that's pretty, I guess it's the most symmetric out of all of these. And before, the symmetries we were considering, reflections and rotations, they were discrete. They were just doing one operation and doing another operation and so on. But here, if you consider rotations, you could maybe start here, and you could rotate the circle about this angle theta and make it rotate, and it would still look like the original circle. But theta ranges from a whole continuum of values. So there's a much nicer symmetry here. It's like a continuous symmetry. Like you've parameterized your symmetry by this variable theta, and theta could be 0, pi over 2, a rotation 90 degrees, 180 degrees, 360 degrees, pi degrees, and yeah. Now, symmetries in physical systems, Newton's law is pretty popular, pretty useful. And so this is Newton's gravitational law. And you would see that in describing this in this equation, if we use polar coordinates, which is, so if these are our 3 dimensions, then you could describe a vector here by giving this the distance from the origin. You could similarly describe the angle it makes from the x-axis, the angle it makes from the z-axis, and so on. And these are our polar coordinates. And in polar coordinates, this equation, it only depends on r, and theta and phi do not appear in the expression at all. So if you imagine, if there's if the Earth rotating about the sun, then the force on it, assuming an ideal circular orbit, it shouldn't depend on where it is in like the angular displacement. So the force is rotationally symmetric, and rotations would leave this law invariant. Even if you rotate by an angle of theta or phi as to where you are, you would still find that the force is the same. And symmetries are nice because they really help solving problems. They really help us to solve problems, because they make the computation or just the process of using the equations of motions and finally determining the expressions of like my x coordinate, my y coordinate over time, they make that much easier. And for example, again, taking the motion of planets around the sun, there's a rotational symmetry, and we can just say some really nice things about angular momentum. Angular momentum, essentially, it's like a measure of it takes into account the velocity of the body and the distance from where it's feeling the force, and it helps relate those two. So you can so once you have this connection, you can use this elsewhere, and it's like an additional constraint on your system that these two are connected. There's a relationship between them, and that would really help simplify the problem. And naturally, in math, if you want to study symmetries, we use group theory. A group is set G with a binary operation star. You could call it multiplication, addition, but just more generally, any binary operation, such that if you pick any two elements of the group and you operate on them, you use the binary operation on both, the new element that you get would still be in the group, and this is called closure. Then there's an identity element, which is if you consider the binary operation with an element of the group and this identity element, it would give you the same thing back. And it doesn't matter in what order you apply that in. Then there's associativity, which is this, which is the brackets don't matter, though, as long as you multiply stuff looking in a particular order, it would be the same thing, and the brackets don't really matter. And then a very important property that for every element in the group, there's an inverse, which is if you multiply those two elements together, you get the identity. And some examples of a group are the integers with addition. So if you add two integers, you get an integer. You can take a negative on the integer, and that will be the inverse. It's associative. It's you have the identity, which is 0, and so on. Then you have the cyclic group, which would be, for example, the integers mod 3, say, or you can take any natural number, and this group is just 0, 1, 2. You can write it like this, and the operation is just addition. So you can add 1 to 0, and you can add 1 to 1, and you can add 1 to 2. But after a while, they cycle back. So if you add 1 to 2, that would give you the identity back. So there's sort of a cyclical property. That's why. Then there's other examples. For example, the dihedral group. It's the group of symmetries of an n polygon, and like we saw with polygons before. Some other concepts. So the generator of a group. The generators of a group. It's a subset of elements of the group, and the idea behind this is that can you find maybe a smaller set of elements in the group that if you perform the operations repeatedly, you can eventually find every element in the group, and that's precisely constitutes the set of generators of the group. So a very interesting example is the cyclic group, because if you consider the element 1, and the operation here is addition, you could keep adding 1 again and again. You could do 1 plus 1, say n equals 3 again, just for simplicity. You will get 2, and then if you do 1 plus 1 plus 1, you will get 0. And in this way, we were able to generate all the elements of a group. And you can do this for higher n also. And this also lends to something called the presentation of a group, which is if we want to just provide some set of rules that this is how our group is going to behave, and provide the generators, essentially the building blocks of the group that which you could use and then make the entire group, that would constitute a presentation. So here you just have one element, which is 1, and then you could so representing the relation here is that if you add 1 3 times, it cycles back. So that's a relation, and this way you'd be able to get 1, 0, and 2. And then another concept is group action. So my purpose with sharing these concepts is just we will see them appear some in places later in the talk, and so it's just nice to kind of have like some background on what they are, and just have a motivation of what they're telling us about. So
Yeah, just as a context thing, some of the people here at the talk have seen the automorphism group of a vector space. Right, it's the general linear group of a vector space.
Mhm.
So maybe if you're talking about group actions and groups, that might be a nice example, but if it's not in your slides, don't worry.
Right. Thank you so much. Yeah. So right, a group action. And so if you have a set, then you could a group action is a function which takes in an element of the group, an element of the set, and gives you another element of the set. And the properties that we want it to have are, if you apply the identity to that element of the set, it should give you the same element back, the element of the set. And there's a nice compatibility between the group action, between the group action and the operation of the group, is that if you act on an element of the group, element of the set, and you act on it with another element, there's it would be the same as taking the result of the binary operation of G and H and acting that on set S. Now, with that out of the way, we can see, we can try to find some of the motivation behind how some of the problems that we encounter in physics might naturally lead us to finding the tools in math that would need to solve these problems, and just the motivation behind why we're doing this. So originally, again, Newton's laws, they laid kind of the groundwork for all of physics. And the one equation to rule them all is force equals mass times acceleration. And usually when we're solving, when we have a system and we want to see how it behave, a general problem solving strategy is you analyze the forces. Say, for example, there's just an incline and there's a block, there's gravity acting downwards. And then you want to see how this would behave. We know that the block would slide down, but we analyze the forces. We set up a coordinate system, and then we, and we would kind of try to break down the forces into this along these orthogonal axes, and then along each axis, we would try to add the forces together, equate them to a net force, and that would help us find the equations of motions. Again, that's how which essentially tells us how the system behaves. Now, there are some restrictions on when Newton's laws are applicable, or I guess the rules of sort of where they're most useful, and using them in inertial frames, which I will, so inertial frames essentially are frames which travel at a constant velocity. There's no concept of acceleration there, and it's a weird thing. So there's still the point is that there are restrictions on where these would give you the correct results, and where you might have to adjust some of the notions a bit to get the right answer. And then they're good for simple systems just like this. You can pretty quickly solve for the equations of motion. But as your system gets more complicated, things get out of hand very quickly. So if you have a general pendulum, sure, Newton's laws would be a pretty slick way to just see how the pendulum would behave. So if you maybe slide the pendulum aside, then it'll swing back and forth. But if you have a spring and that acts as a pendulum, it makes things much harder. And it would be pretty hard and would be pretty tedious to use Newton's laws to find the equations of motions. And then as an example, just to hit the point home, if you have a system like this, I would feel sorry for you if you had to use Newton's laws to analyze this.
What is it a picture of?
Sorry?
What is it a picture of? It looks crazy.
So these are three connected pendulums, and there's a spring acting on the bottom pendulum. So yeah, so you'd have to keep track of all of these angular displacements, and yeah, just too many variables. Yeah.
I see.
The block on the top attached to the ceiling. So at the end of that first rod, you have a 4. Now that 4 is also attached by a rod to a second 4. That would be a B. And there's a third 4, C. Similarly, a C is also attached to that horizontal spring.
Oh, okay.
Yeah, there's 3 balls, 3 rods, and
Terrifying.
a spring. This is
Something
very-
only a physicist would love. Okay, got it. All right.
Yeah, I'm sorry. I should pay more attention to. I should make sure that people are following along. I'm so sorry. Yeah. So, and here we switch to the Lagrangian formalism of solving things, and just as a brief overview, like I said, you have to use certain inertial frames, which are coordinate systems essentially, which from a reference frame move with a particular velocity, which say it could be the Cartesian coordinates. So you're standing in one frame and maybe a car is driving by and they have another frame, but it's going by at a constant velocity. Then Newton's law is perfectly fine. But if things have acceleration, then yeah. But here with the Lagrangian formalism, you can more generally describe your system with just literally generalized coordinates, which would just tell you about the state of your system. And just like we have velocities for the coordinates, like we had them before, we would have generalized velocities and how those coordinates change. Then we, with magic, not really, we define this function called the Lagrangian, which is defined as t minus v, and t here is the kinetic energy, v here is the potential energy, but again, just the definition. Then there's something called the principle of stationary action that okay, so the coordinates will tell you where your system is now, and then eventually you can find out the path the system will take. All of these coordinates, they depend on time, and if you specify at each point in time what the values of these coordinates are, you can just imagine that that's a path that your system will take. Then the principle of stationary action says that the path that the system takes will extremize this integral. And with some calculus of variations, you can derive these equations. And once you've figured out the Lagrangian, you can just take derivatives, and that would give out give you the equations of motion. So, and this is easier because before with Newton's laws, we had vector equations. We were resolving forces along orthogonal axes, components, and then equating them. But here we're dealing with scalar functions, so everything is much nicer. Now this leads us to, I guess, a requirement, a want, that what would be the setting to study physical systems in this way? How would you describe the state of the system? And again, we use generalized coordinates, which are the parameters which tell us what the system is doing at this point in time and how it's behaving. And they determine its configuration. And this space, which that's spanned by these coordinates, is called the configuration space. As an example, just a particle moving in 3 dimensions, you need 3 coordinates, x, y, z, to describe its motion. So its configuration spaces are 3. And if you have n non-interacting particles, then each of those has 3 dimensions to move in, and they don't interact. So very generally, the configuration spaces are to the 3n. So you need 3n numbers to describe at every point in time how your system is, what your system looks like. But we have systems with constraints, and studying things like this, sure, a problem where you have n free particles might be useful, but there are a lot more problems which are useful, which have some constraints, which have some more information on how, on a specific type of information with how it's behaving and how it's interacting with its environment, or there are interactions between the particles and so on. And those are some of the constraints. And these might come from the problem itself. So if the particle is, so for example, we saw the example of a block on an incline, and that's a constraint. The block will move along the incline. It can't sort of fly up from the incline, but it has to stick to the incline and go down, and that's a constraint. Or like we discussed, there are symmetries in problems that we might find, and then we can use those to impose constraints. So like with the gravitational law, things were rotationally symmetric. So that's another constraint where we can relate angular momentum on the motion, the angular motion, and the motion, which is the distance from the origin, and so on. And yeah. Now, so an example of this would be a particle, which is like a pendulum, but this pendulum is free to rotate in 3 dimensions. So it's pivoted at the origin, but so its distance from the origin is constant, but it can move in 3 dimensions. So here you might realize, do we really need 3 generalized coordinates to determine the state of the system? Like, do we again need to provide the x, y, and z coordinates to analyze this? But where you might realize, again, the constraint is that the distance of this particle from the origin is fixed. So you can literally take that for granted, and you just need 2 angles to specify the state of the system, just where it's lying on the sphere, in the sense that you just need 2 angles to once you set up your coordinate system, say this angle from the x-axis, this angle from the z-axis, and that will help you determine the state of your system. And then the configuration space is not the entirety of R3, but the subset of coordinates that define points in the sphere S2. So this is a lower dimensional object. And what might this be mathematically? Well, manifolds. Manifolds, generally, they're spaces which resemble Euclidean space near every point. So if you've taken a course in multivariable calculus, you might recall from there, or if you have done manifolds there, or otherwise, I guess informally, we can say that just like we study curves not only in R1, like not only as subsets of the real line, but we can study curves in R2 or R3 and surfaces in R3. So, and higher dimensional analogs of these would be with appropriate properties manifolds. So S2, for example, in R3 is a manifold. And informally, if you're close enough to a point, you could just keep zooming in and it would appear like a surface. So it's a 2-dimensional manifold. Not the most rigorous argument, but just as motivation. Now, I guess I wanted to take some time to see how manifolds would be, just a short interlude into how manifolds would be used to describe the state of the system. And again, like we considered this system where we just have an object pivoted to the center or to the origin, we just need 2 variables to state its to tell what the system looks like at this point in time. And like I mentioned before, you could imagine that the state of your system could be described over time as a path. Like at each point in time, it tells you what coordinate values there are, and then you could just look at these values at every point in time, and then trace that curve through space, through the configuration space. And again, if you need all 3 coordinates in R3, for example, then you would have a curve going out in R3. But more generally, not more generally, but in this case, because we have some constraint, our particle is constrained to lie on a sphere, that curve would be restricted to a manifold. And right. So manifolds, there are some properties that you can define manifolds, I guess, in multiple ways, but one way, and especially I'm taking a multivariable calculus course right now, and the way we define it is to consider maps from Euclidean space to a set in Rn, which have certain nice properties, which are regularity, which are how differentiable, depending on how differentiable the function is, if it's CR or C infinity and so on, and then you could describe what are called coordinate patches onto the manifold. And for example, with the case of a sphere, actually, yeah. if we consider the circle S1 and R2, you could consider a map from 0 to 2 pi and going on to the sphere, just but not this point, and then you could that map would be described by cosine of t sine of t, and that would map this interval onto the sphere here, but just not this point. And in a similar way, to include all this point, you could define this map not from 0 to pi, but minus pi to pi. And then you would exclude this point, but then similarly define a map here. And in this way, you've managed to describe the set with through a map, and this is in R1. This is a subset of R1, but our manifold lies in R2. And this function is particularly nice. It's differentiable in both components, so that's a property. And there's another property which is related to the derivative of this function, which is another thing. So, and that takes care of the fact that manifolds can't have sort of like kinks. Yeah. And then just as an illustrative, this sort of describes how you might look at the globe, and then you might patch on different parts as flat surfaces from just if you were close enough, then that would seem flat enough, and then you could make a whole map out the whole globe. Then you might also wonder that to describe the state of the system, you don't only need to know where you are right now, but you also need to know where you're going. And that's what velocities help us do. And there's a way to also take this into account in this formalism of using manifolds to describe physical systems. And that's the concept of tangent spaces. And essentially, what we're trying to do is on a manifold, say our sphere, we try to provide, we try to imbue each point with a sort of vector space structure, so that you could imagine this plane, which is tangent to the sphere, and then you could imagine that if a particle was moving on the sphere, it would have a certain velocity vector, and that would lie in this space. And this is a figure from a textbook, where if you sort of consider this map to go from this subset of R2 to this subset of R3, which is a manifold, then you could consider a path and consider the velocity vector. At this point, if you have a path going from, if you call the subset A, and then you could trace that out, and then similarly you could use a map to the map that we, for example, a map like this, you could that would help you go from this space to this space, and you could similarly define a velocity vector which lives in a space like this. Now, finally, we try to study Noether's theorem, which tells us that the symmetries of your physical systems, such as you might imagine that you have a particle moving in free space, and then you would want that the laws of motion, how your particle is moving, if it's moving at a constant velocity, say, they shouldn't change if you shifted your origin to the left a little bit, or maybe you rotated it, because this case is pretty symmetric. It shouldn't matter what your reference frame is or how you measure your or what coordinates you place on this. And that tells you that for every symmetry you get a conservation law. And so our Lagrangian again was a function of the generalized coordinates, the generalized velocities, and time. And the transformation of coordinates, this change in coordinates, we describe, say, with one parameter. And then correspondingly, that would change our Lagrangian to be a function of these new coordinates. And then the velocities of these new coordinates. And then you can use calculus of variations with some tools and the Euler-Lagrange equations, which were shown before, to get this. You can derive this explicit equation. And as you can see, this is a time derivative. And it's saying that the time derivative for this quantity is 0. And that's precisely what conservation is, that a quantity doesn't change over time. And an interesting thing to note here is this invariance of the equations of motion, because the Lagrangian helps you derive the equations of motions through the Euler-Lagrange equations. If you want to consider the invariance, that even if you change the coordinates, your equations of motions don't change, you'd want to consider how this parameter, which defines the change in coordinates, changes your Lagrangian. And here, if you want on the symmetry, you don't want your Lagrangian to change. You want this change in Lagrangian with respect to this parameter to be 0. But an interesting thing here is that this derivative is evaluated at lambda equals 0. And this is something that you would want to deal with, because this is easier to deal with, because say you have a translation or rotation, then studying an entire translation studying just a small translation, an infinitesimal translation, should give you as much information as studying an entire translation. And to have this convenience, we just imagine that we're making an infinitesimal change, and we're seeing how that's affecting our Lagrangians or equations of motion. And we'd want the Lagrangian to be invariant, which is why this derivative is 0. And we'll see how this infinitesimal change factors in. And then the second part of Noether's theorem, which is a bit more mathy, but it's this definition, which is quite complicated, I would agree. And if you see this and if you feel that this is, it is quite a lot. And so in this talk, we won't analyze this entire thing, but again, we coming from the point of view of how to describe our physical system, and that now that we're trying to use Lagrangians to do this, and that we want to figure out how symmetries of coordinate transformations lead to conservation laws. We want something that would help us not only that not only helps us study these symmetries, but also something which are continuous, because translations are continuous, rotations are continuous. Like your physical system would have continuous symmetries. And here we see that an important concept that would come to help us is a Lie group. And so for the rest of the talk, we'll try to study what a Lie group is and figure out why this is a nice tool to help us solve problems. So a Lie group ties together both these important concepts of being group and a manifold. A Lie group is a manifold which is equipped with smooth group operations. And by that, I just mean that, remember when we had a binary operation, so that you take two elements, you do the binary operation, and that's still an element of the group. That information is just contained in this function. And what this is, and then we also wanted inverses for each of our elements, so that information is contained in this function. And there's an identity element, but we also want these two structures to interact, and that we impose by saying that we want these operations, the binary operation and the inverses that we want from our elements, we want these to be smooth, which is we want them to be continuous and maybe even differentiable, and higher degrees of we want higher degrees of differentiability, and essentially for them to be nice enough. Then, for example, R3 with the addition of vectors is a Lie group. So the addition of vectors is the binary operation here. The identity element is just the origin 0, 0, 0. You have inverses because you can just negate your each entry of the vector, and that would give you the identity. And then these operations are also smooth because entry wise you can figure out the continuity and differentiability. Then the group of rotations about the origin in R3 and the operation here would be composition, is also a Lie group. And then if you choose a basis for R3, then the rotations are described by orthogonal 3 by 3 matrices. And orthogonal, or the condition of orthogonality, is that the transpose of your matrix is the inverse. So that gives you the identity. And the determinants of these matrices is precisely 1. Then there is an additional concept which comes together with the notion of a Lie group, which is called a Lie algebra. An algebra is a vector space V, which carries along with it an additional operation, which is a bilinear function. A bilinear function meaning it will pick 2 elements from the group and it will give you another group. But so we have seen something similar, which is an inner product. So like the Euclidean space with the dot product, that is a bilinear operation. It's linear in both slots, but what it does is it takes 2 elements of the space and it gives you an element in the field, which is the real numbers. So we don't want a number, we want an element of the space itself. And that's what this bracket operation does. And more specifically, a Lie algebra is, so like we talked with manifolds, when we had a sphere, you could find a tangent space. The Lie algebra is the tangent space of the manifold G, the Lie group, over the identity element. And again, that this Lie algebra is equipped with the bracket operation, which takes in 2 elements of the group and gives you another element. Which takes 2 elements of the Lie algebra, and gives you another element. And an example here again would be R3, which R3 the Lie group, and the Lie algebra would be R3 again. And you might wonder what operation can we imbue on this R3 with the origin. And you might wonder what operation can we imbue on this that takes in 2 elements and gives you another element, and that is the cross product. So you have 2 vectors, and that gives you another vector in R3. And this bracket also has certain properties, but we don't really, for the purposes of the talk, it's not really necessary. Right, and the connection between using Lie algebras and Lie groups is that we wanted to analyze our system, the symmetries of the system, which would be continuous. So like we looked as in the case of the circle, which are rotations, and we also want that to kind of go hand in hand with how we're describing our system, which is on a manifold. And and then we looked at Noether's theorem, which in the first formulation, we saw that studying a symmetry we can also study infinitesimal symmetries, which is we don't probably need to translate by, I don't know, 5 kilometers. We can make an infinitesimal change and still study the symmetries of our system. So here I would try to give you a sort of plausibility argument of why a certain symmetry, of why studying infinitesimal symmetries would help you study a symmetry itself. So now we can consider rotations in 2 dimensions. And I guess the usual way, so rotations are a pretty common form of transformation in physical systems. Again, like we saw in the case of Newton's laws, you can rotate around, like, so if the Earth is going around the sun, you can rotate your frame of reference, but still you'd expect the force the force won't change because it only depends on the distance and the r coordinate and our polar coordinates. Now, usually you would, if you wanted to figure out how can I describe rotations like we saw before, we can use matrices once we have established a basis on the vector space, and we're considering R2 here. So our basis would just be E1, 2. So now we can describe rotations with two by two matrices. And there is, you can use trigonometry to figure out what a rotation matrix should look like. So if this is your coordinate system initially, and you wanted to describe a rotation of your coordinate system, say by some angle theta, you can figure out how this change would affect the components of a vector, and then you can put those in a matrix and then figure out the matrix. And some of us would be familiar with this. You may or may not have seen this. And a rotation matrix in 2 dimensions looks like this. But say you were studying rotations in a math class, and maybe trigonometry is not the thing that you find the most interesting. So you kind of zoned out. How would you manage to figure out what the rotation matrix looks like, and eventually, because rotations are associated with these 2x2 matrices, how a rotation should look like, only on the basis of these small infinitesimal rotations?
If you were taking H22, you'd write down the standard basis and you'd see what the rotation does to the standard basis.
Right. So, sorry, could you repeat that?
So you'd write down the standard basis and you'd see what the standard basis of R2 does.
Oh, how the matrix would affect just the standard basis?
Sure, yeah.
Right, but still, I guess I should put this more clearly. Sorry about that. But what we're trying to do is figure out how we can determine the form of a rotation matrix in general, whatever rotation it might be, just on the basis of small infinitesimal rotations. So the matrix acting on the basis vectors would tell us how the rotation would act on any vector, but we want to figure out the matrix itself from just this notion of how studying a small rotation should be equivalent to give us information about rotations in general.
Would you study what it does to the tangent space?
What it does to the tangent space. So the argument I'm going to give now is not that complicated, but perhaps you could use something like that to figure out. So, for instance, if you're studying an infinitesimal rotation, say you wanted to describe your matrix in terms of a parameter theta, which is just you have 4 entries and each of those depends on theta. You'd want that when theta is 0, you do nothing. It should precisely be the identity. So a small infinitesimal rotation is very, very close to the identity. So if you have a matrix like this, and the entries depend on some parameters, the parameter theta, you'd want that it looks like the identity for very small, for if the angle you're rotating by is 0. And now this is a bit this is sweeping things under the rug, but then you could say that, okay, what if I consider rotations up to like only a linear order on my entries, which is a rotation by an angle of 0 should look like the identity. But if I parameterize my rotation matrix for a very small angle, where M is just any matrix, by just a linear order theta, so that when theta is very small, if the entries of my matrix depend on theta squared or higher order terms, you would just ignore that because they would be even smaller. So you could sort of maybe argue that an infinitesimal rotation matrix should look something like this. Now we know that rotation matrices are described by orthogonal matrices like we saw before, which means the transpose of a rotation matrix is its own inverse. And rotations are invertible. If you rotate something by an angle theta, you can rotate it by an angle minus theta and get back the identity. So how about we impose that constraint here? So we'd want, which is, and we know that if we have two matrices and we apply the transpose of those matrices. It's just A transpose plus B transpose. And the transpose of the identity is just the identity. So here we apply the transpose to the matrix M. And this would be.
You should go to the left. You should go to the left.
And again, we see here that we do have an expression, but we start seeing terms of which are parameterized in terms of a higher order of theta rather than just a linear order. And because we're considering very small rotation, we can effectively say that this is going to be very small, so maybe we can just ignore it. But we just stipulated that the transpose of a rotation times the rotation matrix should be the identity. So we want that this equals the identity matrix. And that would mean that theta that is 0. And so assuming you do make some change and theta is not 0, but it's still very small, you would just get this relation. And yeah, and you would see that this describes, this is a property of matrices, which is precisely that the matrix is skew symmetric, which means it's the negative of its own transpose. And so since we're considering 2 by 2 matrices, if we have something like this, and we want it to be equal to negative of its transpose, then A equals minus A, D equals minus D, which means A and B should both be 0, and then B equals minus C, which means a skew symmetric matrix in 2 dimensions would essentially look like this. So, and then this tells us that this matrix M, which is sort of, now that we parameterize a rotation matrix in terms of a very small angle theta, and we're measuring how that infinitesimal rotation should act. And M is a matrix that helps us achieve that helps us determine what sort of behavior of that matrix should look like. And then we can consider the specific, because we can just factor the B out, this is just a constant. We can look at now this parameterization of the matrix was essentially I plus theta M. So you would see that this is 1 theta minus theta 1. Well, approximately. Now, again, the actual rotation matrix.
Sorry, Aditya, hold up. We are now getting right to like the top of the hour. It's 1:59. Usually we end seminar at 2. So if you have like closing remarks, important things you want to end on, that would be
Right.
nice. So
Right. So I guess just to hit the point home, this was the matrix. This was kind of the punch of the whole thing. And you can sort of see that if you did it, this resembles the Taylor expansion of cosine theta and sine theta. So this is saying that if you started considering a higher order terms as well, you would get that each of the entries is, you would get the Taylor series in each of the entries of cosine theta, sine theta, and then you'll eventually be able to construct your entire rotation matrix. And this shows that considering infinitesimal transformations would also help us study the actual transformation. And then eventually, when we're considering a continuous symmetry of our physical system, this would prove to be really helpful. And here, Lie groups and Lie algebras come in useful, because Lie algebras, so here, for example, the Lie algebras, which form the tangent space on the identity of your Lie group manifold, they would help generate all of the matrices. So I guess that's a good place to stop. And thank you so much for attending this talk.
sweet. Thank you for that talk. That was awesome. It was nice to have a physicsy talk. Next week we have a kind of statsy / applied math talk about the advantages of working remotely. So Professor Lisa Jeffrey, one of our co-organizers, had some students do some research on this. So that will be up next week. Before we end off, are there things people want to ask? Yeah. Allard has figured out a next level complex way of doing this.
Yeah.
Sweet. Thank you for that talk. That was your first talk. That was an awesome first talk. Before people rush out the door, the people in room, I ask you to fill out your name and email so we can get more muffins. Aditya, well done. That was an awesome talk for a second year. Thank you so much. And we'll see you next time at the undergrad summit.
Can I get a pencil?
Bye-bye. Thank you.